This lesson is going to talk about regression and the correlation coefficient. So the first thing we need to talk about is what we actually mean when we say regression. Regression is the line or curve that's going to explain our scatter plot the best. It could potentially pass through a lot or some of the points, but it is also possible that it will pass through none of the points. And the line or the curve that we calculate when we do regression is going to be a prediction model, and then the scatter plot is our actual data that has been collected. So it's possible that you will see some questions that ask you to compare the actual with the predicted, and that equation is our prediction equation. So we're going to see how to do this with Desmos today. So this is our first example here. I already have my data in Desmos in a table. So go ahead and pause the video and put this meal cost in X and tip in Y. So now you have your table in Desmos. We're going to come into this second line here, and we're going to do our regression right in Desmos. I'm going to do Y1, and then I'm going to do it's called a tilde. It looks like the funky little squiggle. If you hit Shift and then the button next to number 1 underneath Escape or in that top corner, that will get you the tilde. And then I'm going to look at my graph here. These points look like they are in a line. It looks very linear. So I'm going to type in a linear equation. So I'm going to do mx. Now, since I'm pulling from my data, I have to put x1 and then plus b. So you'll notice it shows up with this line. This is my prediction model. And then the green dots are the actual information. We're going to talk about what this means in just a second, but we want our parameters. So our equation is going to be y equals 0.157. We'll do 3 decimal places here. And then that's my slope, so that's going to be multiplied by x, and then minus 0.299. So I'm going to come back to my document camera here, because what it's asking us to do is they gave us a tip, so they want us to determine the cost of the meal. So they gave us a y value. So $6.40 was the tip. And they want us to work backwards and predict what the meal cost was. So I'm going to add 0.299 first. So I'll have 6.699 equals 0.157x, and then I'm going to divide by 0.157. So my meal cost would have been $42.67. And then that's my equation. I didn't realize I gave us a line for it. Whoops. All right, so that's our first one. That was linear because of how the graph of the scatter plot looked to us. Here's our next one. Now, I couldn't fit this in all one table, so all of this data is one table in our Desmos plot. So go ahead and pause the video and put that into a table. I've already done that, so here is my table. And you'll notice these do not look linear. This looks like an exponential curve. So instead of typing in a linear function, when I do y1, I'm going to do y1 and my tilde. And then since this looks linear, I have to do since this looks exponential, not linear, I have to do an exponential equation, which is a times b raised to the power of x1, because I'm pulling from my data. So then here, this is my coefficient a, and this is what goes in the parentheses with x as the exponent. So my equation would be y equals 0.832 times 1.924 to the power of x. All right, so I'm going to leave this up for just a second because I want to use this statistics piece here. All right, so talking about our correlation coefficient, we talked a little bit about these numbers yesterday. We could have a number that was between 0 and 1. The closer it is to 1, the stronger the correlation. The closer it is to 0, the weaker the correlation. And if it's 0, then there is no correlation. So if we're looking at a linear relationship, I'm looking at the correlation coefficient of R. So these should look similar to what we looked at yesterday. Weak, they're very spread out. Strong, they're very close to being in a line. And again, I'm looking at that R value only if it's linear. If it's not linear, I'm going to look at R squared. So if it's quadratic or if it's exponential, I'm going to look at R squared. And this tells me the percentage of the data that is the closest to the actual regression equation that we've been given. So the higher the decimal, the closer it is to 1, the better the line is or the curve is as a predictor for that data. The closer it is to 0, the worse that function is to use for predicting the data itself. So if we come back to that last example, if you look here, my R squared value is 0.9927. That means 99.3% of the data is well explained or well predicted by my model. That is excellent. 99% of the data being explained means it's pretty close to being perfect. So we're going to go on to that next example that's above that R squared slide. The number of hours a student spends studying and the score they receive on the first 5 math tests. So pause, put that data into a table, and come back when you're ready. And I have mine ready to go. Now I do need to zoom out. All right, let's see. So this part here looks pretty linear to me, so I'm going to test a linear function first. And when I look at my R value here, it's 81% accurate. The R value is really close to 1. So I'm going to say, let me just check and see if exponential might fit better. All right. Looking here at the r squared values, this is 0.812. This is 0.814. So I'm okay in this case sticking with my linear function. So I'm going to write down this equation. Y equals 2.912x plus 86.794. I'm going to come back to my screen. So this is the equation we just found. They're telling us that our y value is 94. The person received a 94 on the test. So this is very similar to the one we did before. Oops. Oh, my Lanta, I'm writing everything backwards today. And I'm going to go ahead and start solving this. So I'm subtracting first. So 7.206 equals 2.912x. And then dividing tells me they spent about 2.5 hours studying. And yes, I did round in that case.